Hello, this is Stat135, Lecture 11. On Friday, you have a quiz where you'll be asked to calculate an MLE, calculate an asymptotic variance of an MLE, and also find a 95% CI of an MLE. Last time and the times before, we have been seeing that that an MLE estimator has many good properties. It has equivariance, consistency, it's asymptotically unbiased and normal and efficient. In fact, an MLE estimate for large N is approximately normal theta 1 over the Fisher information. And today what we're going to do is in section, finishing section 8.7, discussing the MSE of an estimator, and then beginning section 8.8, sufficiency of a statistic. So MSE is an important measure for how good an estimator is, and it's defined as the expectation of the difference of the estimator and the true parameter squared. And it's essentially the average distance between the estimator and the true parameter. And an important property is that it's the variance of the estimator plus the bias of the estimator quantity squared, something you'll show for homework. So you can have, with the same MSE, you can have an estimator that has high variance, low bias, or low variance, high bias. Here's an example. So, here is an example of two unbiased estimators. X1 to Xn is IID Bernoulli. So X1 and the sample mean are both unbiased. So to calculate the MSE, then I just need to calculate the variance. And the variance of the sample mean is less, and hence the MSE for the sample mean is less. The sample mean is the MLE estimator, by the way. So among all unbiased estimators, the MLE for large sample size has the smallest possible MSE since it's efficient. If you remove the constraint of being unbiased, however, you can lower the MSE by finding an estimator that has a very, very small variance. On to sufficiency. So sufficiency has two primary motivations. One is its use in making estimators better, having estimators with a lower MSE. That's called the Rao-Blackwell theorem. And the other is its use in data reduction. So for the purpose of inference, you may not need all of your data, but just a summary statistic of your data, such as the sample mean or something like that. And so we'll be discussing that. So let me give you examples of these things. So the Rao-Blackwell theorem says that if you have an estimator, we're gonna condition it on this thing called a sufficient statistic, and take the conditional expectation, and that will be an estimator that has a smaller MSE. So it's strictly smaller unless your original estimator is a function of the sufficient statistic. In which case you get equality instead of inequality. So here's an example. So if X1 to Xn is IID Bernoulli, it turns out that the sum of these xi is a sufficient statistic. And so we're going to start off with just the first. So X1 is our initial estimator, and we're going to Rao-Blackwellize it. And the Rao-Blackwellized estimator is the sample mean, which we know from above has a smaller MSE. concerning data reduction, the factorization theorem is what you need to understand here. So the factorization theorem says that a necessary and sufficient condition for a statistic to be sufficient for a parameter theta is that the likelihood factorizes as a function of the sufficient statistic in theta and a function just involving your data. So for the purpose of finding the theta that maximizes your likelihood, from the factorization that we have, we can see that what we need to do is optimize G. So G, which is a function just of t and theta. So the h x1 xn is just a number independent of theta, so it's not important for the purpose of optimizing, finding the theta that optimizes the likelihood. So what we need to optimize the likelihood is G, which is a function of your sufficient statistic and theta. So that is why if we have a sufficient statistic, we don't, once we collect our data, we can basically find our sufficient statistic and then throw away our data for the purpose of finding an estimator for theta. So one way to think about sufficiency, if say that your sufficient statistic is the sum of your x1 to xn, then that creates a partition of your outcome space. By outcome space, I mean all the different values x1 to xn that your random variables take. That's a high dimensional space, and we can just reduce it. If t is just the sum of those xi, then we can just reduce our outcome space to a single dimensional space, right? Where all we care about is the different values of t. So all those xi that have the same sum get collapsed to a single equivalence class. So to define sufficiency, we start with the definition of a statistic. So a statistic is just a function of your data only. So for example, sample mean, the third observation, the minimum of your x1 to xn, and so on. It can't have any parameter in it. Definition of a sufficient statistic is that x1 to xn conditioned on t doesn't depend on theta anymore. So somehow conditioning it on t removes dependence on theta. So in some sense, t contains all the information about theta. What this means in terms of the joint density is that when we condition our joint density on t and theta, it removes the dependence on theta. So let's see an example here. So if we have x1 to xn IID Poisson theta, so here is the joint. So the joint density. We have the joint density here, and we're going to show that the sum of the xi is a sufficient statistic. We're going to use Bayes' rule, and here's essentially Bayes' rule for densities. And what we want to notice here is that So if little t is the sum of these x1 to xn's, then that is essentially t equal little t is a redundant condition here. It's a redundant requirement. So if we have x1 is little x1, x2 is little x2, and so on, then because of that, big T is T. So you don't need to write that. And so we can write our Bayes rule a little more simply, where now the numerator doesn't have T in it anymore. And writing out what the numerator is using our formula for our Poisson formula, and the fact that T is Poisson n theta because T is a sum of independent Poisson thetas. So we can write out what the distribution, what our density Ft given theta is. And an amazing thing happens. All of the thetas drop out, and we get something that has no dependence on theta. So that would show you that T is sufficient. So I can just illustrate this briefly by saying, suppose that someone asked you, what's the chance of drawing 1, 3, 4 from a Poisson theta? So the answer to this is, well, it depends on what theta is. I can't answer that unless you tell me what theta is. But if someone asked you, what's the chance of getting 1, 3, 4, if I know that the sum is 8, then you can answer the question. So the answer would be given by this formula.